Welcome to Lecture 12, in which we will continue our discussion of Karnaugh maps. But before we do, I want to touch on a question that one student raised during one of our recent classes. It's a very good question, and so I want to show it to you. Suppose we have a function f4, which is defined as being the product of the max terms capital M0 and capital M5. And suppose that we were asked to find the minterm expansion of F4. Well, you might think about this yourself and think about what the answer would be. And if you do, I hope that you will see that, although I wouldn't be too surprised if you don't, because it's a little tricky, I hope that you will see that really you can't answer this question. Let me illustrate what I mean. Some people would say that the minterm expansion of F4 is the following. They would say little m 1, 2, 3, 4, 6, and 7. But another person may say that the correct answer is that the minterm expansion of F4 is 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Which answer is correct? Well, the first answer is correct if F4 is a function of just three variables. Let's say x, y, and z. But the second expression is correct if F4 is a function of four variables. Let's maybe call them w, x, y, and z. So it's important when you're finding these expansions, and really almost any time you're working with a function, it's important to understand how many independent variables you have. So as long as we have this example here, let's go ahead and work with it for a moment. Suppose, and this time we'll spell out the independent variables. Suppose F4 of x, y, and z is equal to capital M0 ended with capital M5, and we're challenged to find all minimal sums. Now, as you're going to see, we've already spent a fair amount of time with Karnaugh maps, and we will continue to spend at least this lecture and probably the next one with Karnaugh maps. This is a very important topic, perhaps the most important topic in this course. And so you want to make sure you understand this. So if you feel like you can go ahead and do this problem on your own, I strongly encourage you to to go ahead and stop the video and to try to do it on your own. But if you don't feel confident of that, then we'll all do it together. So we want to find all minimal sums of this, and I'll just go ahead and show you how I would proceed to do this problem. First of all, as usual, we note the number of independent variables, which is 3, and so the number of cells in the Karnaugh map will be 2 to the third power, or 8. So we're going to have a Karnaugh map that will look like the following. And once again, remember this numbering, the appropriate way to number this Karnaugh map. Now, if you wish, you could go ahead, as we've already noted, and find the minterm expansion for this function. since it's so easy to do, we'll go ahead and say it's the sum of the minterms 1, 2, 3, 4, 6, and 7. And so we know that we will have ones in those cells corresponding to those numbers. Now let's remember what we've said before. This is 0, 1, skip over 2, 3, 4, 5, skip over 6, and 7. So let's put ones in the appropriate cells here. We have a 1, 2, 3, 4, but we don't have 5. However, we do have 6 and 7. So this is the Karnaugh map for the function f4, and now we will proceed in the usual way to try to find all the minimal sums of this function. And remember that we first want to find the prime implicants. Now we have 8 cells, so we first ask ourselves, do we have any groupings of 8 one cells? And the answer is clearly no, because in fact we only have 6 one cells in this problem. So since there are no groupings of 8 one cells, we go to the next lowest power of 2, which would be 4. Do we have any rectangular groupings of 4 one cells? And the answer is indeed yes. We have this grouping right here. Now, we come down here then, we'll draw just a little sketch, and again, this is not mandatory, it's just something I recommend doing. And now ask yourselves, what is the name of this prime implicant? Well, does X appear in the name of this prime implicant? Remember, the only variables that appear in the name are those that are not changing. And along the top row of this prime implicant, X is equal to 0. Along the bottom row, X is equal to 1. So X does not appear in this prime implicant's name because it's changing within the prime implicant. What about Y? Well, Y is equal to 1 along the left column, and Y is equal to 1 along the right column. So Y is constant and equal to 1, and therefore the name, the variable Y will appear in the name, and we'll put a Y there. And finally, what about Z? Well, Z is equal to 1 in the left column, but Z is equal to 0 in the right column. So since the value of Z is changing, it will not appear in the name for this prime implicant. So the complete name for this prime implicant is simply Y. Now, are there any other rectangular groupings of 4 one cells? And the answer is no. So now we go down to the next level, next power of 2, which would be 2 itself. Are there any groupings, rectangular groupings of 2 one cells that are not already completely contained within a prime implicant that we have identified? Well, notice that if you look, obviously there are several groupings of 2 one cells. There's this, we could look at this grouping here, but it's already entirely contained within a prime implicant we've already identified, as is this grouping of 2 one cells, or this grouping of 2 one cells. So all of those we ignore. However, there are some groupings of 2 one cells that are not entirely contained within this prime implicant, and one of those would be this grouping here. Notice, however, as I told you before, I like to look for the difficult ones first, and if you look hard, you'll see that there is another grouping of 2 one cells. There's this one and this one, because remember, again, the right edge of the Karnaugh map is connected to the left edge. So let's do this tricky grouping of 2 one cells first, and then we'll go back to this easier one. So again, we're going to look at this grouping of this one cell together with this one. So I'll go ahead and sketch this. And now we have to ask ourselves, what is the name for that prime implicant? So again, I encourage you to stop the video for a moment if you're still a little rusty on this, or maybe I shouldn't say rusty, but hesitant. But if not, then I'll go ahead and do this together. So, is X changing in this prime implicant? Well, the answer is no. This prime implicant is entirely on the second row, and X is always equal to 1 on the second row, and therefore X will appear in the name. What about Y? Is it changing? Well, in this cell over here on the left, Y is equal to 0, but in the cell over here on the right, Y is equal to 1. So Y is changing, therefore it will not appear in the name of the prime implicant. Finally, over here on the left, we ask ourselves, what about Z? Z is equal to 0 on the left. Z is also equal to 0 on the right. So Z will appear in the name, and it will be Z prime since Z is equal to 0. So that prime implicant has the label XZ prime. And now we go to the last grouping of 2 that is not entirely contained within one of the prime implicants we've already identified, and it's this one here that we've just circled. And I'll draw a sketch for that. And now let's try to figure out the name for that. Is X in the name? X is equal to 0 everywhere along the top row, and this prime implicant is in the top row. So yes, X will be in the name, and in fact it will be X prime since X is equal to 0. Is Y in the name of this prime implicant? The answer is no, because for the left cell, Y is equal to 0. For this right cell, Y is equal to 1, so it will not appear. What about Z? The answer is yes, because Z is equal to 1 in this cell. Z is also equal to 1 in this cell. So since Z is constant and equal to 1, we'll have a Z. And so that's the last of the prime implicants of size 2. And now if we look for prime implicants of size 1, all of those are already contained within pre-existing prime implicants. So that's it. We have no more prime implicants. This is it, just these 3. Now we look for essential prime implicants. And remember that in order to identify essential prime implicants, we first look for essential 1 cells. And again, what is an essential 1 cell? It is a 1 cell that is contained within only 1 prime implicant. So let's just go through these one by one. This is an essential 1 cell because it is contained only within the prime implicant XZ prime. This is an essential 1 cell because it is contained within the prime implicant X prime Z and only within X prime Z. The one right here is not an essential 1 cell because it is contained within both X prime Z and Y. Likewise, this one is not essential because it is contained within XZ prime and Y. But these two, this one and this one, both of those 1 cells are contained only within the prime implicant Y, and therefore, since they are within just 1 prime implicant, they are essential 1 cells. Now, any prime implicant that has at least 1 essential 1 cell, at least 1, is an essential prime implicant. And so we see that our first prime implicant Y does indeed contain at least 1 essential 1 cell. In fact, it contains 2. XZ prime although this one is not essential, this one is. So XZ prime is essential. And finally, X prime Z has this essential 1 cell. So, as has been the case in all of our examples so far, every prime implicant is an essential prime implicant. And therefore, the function f4, as we now look for minimal sums, the function f4, if we begin to write it out, f4 of xyz, remember that every minimal sum that you identify must always have in it the essential prime implicants. So that's what we'll start with, y or x z prime or x prime z. And now that we've written down those, we'll go back and shade in each one. Y takes care of those terms. X z prime takes care of this term, which is already shaded, so we really don't need to shade it again, and also this term. And then finally x prime z will take care of these two terms. And since there are no other cells left, there are no other ones there that we need to account for, then we're done. And we conclude that this is the only minimal sum for the function f4 of xyz. So now let's do our first function of 4 variables. And this problem is in the book. It is problem 5.4. And we'll look at capital F of A, B, C, D is equal to B, D prime, or B prime, CD, or ABC, or ABC prime D, or B prime D prime. And the book asks you to find, well, it asks you 3 things. It asks you to plot the Karnaugh map, and it specifically says to do this without first finding the midterm expansion. And I think that that's a good idea. You don't want to have to always find the midterm expansion for a function before you can plot it on a Karnaugh map. You want to be able to look at the algebraic expression and plot it directly. So we'll go ahead and follow that direction. And then part B of the problem says to find the minimal sums. We will do that as well. Part C of the problem asks you to find the minimal products, and we'll hold off on that part for just a little bit until we get a little more familiar with finding minimal sums, and then we'll talk about using Karnaugh maps to find minimal products. It's a very similar procedure, so we'll see that in the near future. But for now, we want to do that first part of this problem, which was to find the Karnaugh map, and we want to do it without first finding the midterm expansion of this function. Now, this is our first case where we have a function of 4 variables, and so we reason as follows: 2 to the 4th is 16. So we now need a Karnaugh map with 16 cells, and we generally will write that in the following form. It'll have a 4x4 structure. This is an important example for you to pay attention to, because really, if you know how to do this one, I believe that you'll be able to do any of the Karnaugh map problems that we will encounter. Now, we will consider the first two independent variables, A and B, to be on the vertical axis, and C and D will be on the horizontal axis. And now both axes will have the labeling 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. And now let's look at BD prime. Well, the term BD prime will be equal to 1 whenever B is equal to 1 and D is equal to 0. It doesn't matter what A is, and it doesn't matter what C is. We just want to identify all of the cells that have both B equals 1 and D equals 0. So let's think about it in this way. Remember over here on the left-hand side, we have 4 pairs of numbers. In each pair, the first number of the pair represents the value of A, and the second number of the pair represents the value of B. Now, keeping in mind that we want all those cells where B is equal to 1, you can see that B is equal to 1 in these middle 2 rows. In this row, A is equal to 0 and B is equal to 1. And in this row, A is equal to 1 and B is equal to 1. But these are the 2 rows where B is equal to 1. So the cells that we're interested in for this first term, BD prime, they must lie in these middle 2 rows. In all of those cells, B is equal to 1. Now we need to identify in which of those D is equal to 0. And we see that D is equal to 0 in these 2 cells, and D is also equal to 0 in these 2 cells. Now, how did I get that? Well, remember that for the numbers along the top, D is the second number. We have C, D. So here C is 0, D is 0, C is 0, D is 1, C is 1, D is 1, and C is 1, D is 0. So the 4 cells that we have identified here are the only cells out of all 16 cells. They are the only cells in which both B is equal to 1 and D is equal to 0. Now, one more note before we proceed. We're going to go ahead with this problem, filling in the Karnaugh map, and we're going to find that this, now remember, this is a minterm, this A, B, C prime, D. It is a minterm because it is a simple product of all of the variables in complemented or uncomplemented form. This minterm will be represented on the Karnaugh map by one cell. This term that has 3 variables will be represented on the Karnaugh map by 2 1 cells. And this term that we just did that had just 2 variables in it was represented by 4 1 cells. So as we noted before, the smaller the term is in terms of the number of variables, the smaller the term is, the bigger it is on the Karnaugh map, the more 1 cells it has. So just keep that in mind. It's a useful observation. So we go to this next one, and according to the observation we just made, this should correspond to 2 cells on the Karnaugh map, and let's see if that's correct. Okay? Well, first of all, we see that this term will be equal to 1 only in those cells in which B is equal to 0, C is equal to 1, and D is equal to 1. We don't care what the value of A is. Well, one quick way of identifying all of those cells where that's true is to notice, okay, we have to have C is equal to 1 and D is equal to 1, so that immediately tells you that we're interested in this 3rd column of the Karnaugh map, because that's where C and D, that's the only place, right here in this column, that's the only place where C and D are both equal to 1. And now, of those 4 cells that we just identified, and how many is B also equal to 0? And the answer, if we keep in mind that B is the second number in these pairs over here on the vertical axis, we see that B is equal to 0 in the first row and B is equal to 0 in the last row. So we have a 1 and a 1 there. And you will see that in these two cells, those are the only two cells in which B is equal to 0 and C is equal to 1 and D is equal to 1. And notice, as we predicted, this term here, which had 3 variables, is represented on the Karnaugh map with 2 1 cells. That will also be the case here for ABC. If you haven't been doing so already, encourage you to stop this video and try to find the rest of these terms on the Karnaugh map yourselves, and then turn the video back on and see if you were correct. So for this term ABC, we want to know all those cells where A is equal to 1 and B is equal to 1 and C is equal to 1. Well, since A and B are both 1, that tells us immediately that we're interested in this third row of the Karnaugh map. And since we want C also to be equal to 1, that tells you we're interested in these two cells. Now 1 already has a 1 in it, so we don't put another 1 in it, we just leave it as it is, but we also have a 1 in this cell. Now we go to A, B, C prime, D. Well, A and B must both be 1, C must be 0, and D must be 1. And so that, since A and B are both 1, we know we're in this row. And since C is 0 and D is 1, we must be in this column, and therefore we get a 1 there. And then our last term is B prime, D prime. So we want B equals 0 and D equals 0. Well, B equals 0, so keeping in mind that B is the second number in each of these pairs. B equals 0 corresponds to the first row and the last row of the Karnaugh map. And D equals 0 corresponds to the first column and the last column of the Karnaugh map. So we get 1, 1, 1, and 1. We get the 4 corners of the Karnaugh map for that term. And that completes the Karnaugh map for this function. So I hope that you were able to obtain that on your own. And now, as usual, we want to find all minimal sums. So I strongly encourage you to turn off the video for a moment and try to do this yourselves, and then come back and we'll do it all together. So, as usual now, if we want to find all minimal sums, our first step will be to find the prime implicants. And since we have 4 variables in this case, we first ask, do we have any rectangular groupings of 2 to the 4th power or 16 1 cells? And definitely the answer is no, because if you count, you'll see that we only have 12 1 cells in this problem, not 16. So no rectangular groupings of 16 1 cells. So now we go to the next lower power of 2, which would be 8. Do we have any rectangular groupings of 8 1 cells? Well, we almost have one here. If this cell had a 1 in it, then the entire right side of the Karnaugh map would be a rectangular grouping of 8 1 cells. But, of course, we don't have a 1 there, so that doesn't count. Do we have anything else? And the answer is yes, we do. Keep in mind that the right and left edges of the Karnaugh map are connected, and so we have a grouping of 8 cells. It's those 4 with these 4. That is a rectangular grouping of 8 1 cells. This is the first time we've seen anything that large. So we'll draw a sketch. And now you should try to think about what the name of that prime implicant will be. We'll do it now together. Clearly, A will not appear in the name because A is changing. In the first 2 rows, A is 0. In the second 2 rows, A is 1. So the value of A, since it's changing within the prime implicant, it will not appear in the name. Likewise for B. B is equal to 0 in the first and last row and 1 in the 2 middle rows. It's changing, so it will not be in the name. What about C? Remember that C is the first number in each of these pairs of numbers along the top, and in this portion of the prime implicant, C is equal to 0. In this portion of the prime implicant, C is equal to 1. So C does not appear in the name either. The one variable that is constant is D, because D is equal to 0 everywhere here on the left, and D also everywhere here on the right. Since D is constant, it will appear in the name, and since the constant that it's equal to is 0, it will be D prime. So that's how we'll name that prime implicant. Now, are there any other groupings of 8 1 cells? Well, as we have said, almost. If this were a 1, we would have a grouping here. If we had a 1 here, we would have a grouping along the bottom. But in neither of those cases do we quite have what we need. So there are no more groupings, no more rectangular groupings of 8 1 cells. Therefore, we move to the next lower power of 2, which is 4. And we now will look for rectangular groupings of 4 1 cells that are not already completely contained, or that are not completely contained within a pre-existing prime implicant, or a prime implicant that we've already identified. So in other words, this grouping of 4 here, we do not use because it's completely contained within the prime implicant we've already identified. Similarly, for this grouping of 4. Or you could also think of the grouping of 4 that has these 2 and these 2, or these 2 here and these 2, or these 2 and these 2. There are plenty of groupings of 4 that we see here, but all of those we've discussed so far are completely contained within the grouping of 8 that we've already found, and so we don't use any of those. So now let's ask ourselves, where are there any groupings that are not completely contained within it? And the answer is yes. One that we see is this grouping right here. Now, part of this grouping is contained within the previous prime implicant, but part of it is not. And so that's fine. As long as some of it is not, then this does count as a separate prime implicant. So let's go ahead and identify this term. And we'll go ahead and sketch this. And since this is a smaller prime implicant than the first one was, we will expect the name to have more variables in it. And let's see if that's the case. So right now we're trying to figure out the name for this prime implicant that has these 4 cells in the lower right hand corner. So does A appear in the name? Well, A is constant and equal to 1 on those last 2 rows, and so indeed A will appear in the name. Does B appear in the name? No, because B is equal to 1 in the third row, and B is equal to 0 in the fourth row, and since B is changing within this prime implicant, it will not appear. What about C? Well, C is equal to 1 in this column, and 1 also in this column, so in fact it will appear. What about D? No, D is equal to 1 in this column and 0 in this column, and since D is changing, it will not appear. So this prime implicant of size 4 1 cells has a name with 2 variables, and the name is AC. Now, are there any other rectangular groupings of 4 1 cells that are not completely contained within a prime implicant we've already identified? And the answer, I hope you'll agree, is yes. You see this one here, the third row of the Karnaugh map. So let's sketch that one. There's the third row of the Karnaugh map. And try for a moment to figure out the name of that one. I hope that you will quickly conclude that the name of that prime implicant is AB, because A is constant and equal to 1 for all of 4 of those cells. B is constant equal to 1 for all 4 of those cells. But within those 4 cells, we see that C is changing. In the first 2 it's 0, and the second 2 it's 1. And D is always also changing, because in the first one and the last one D is 0, and in the second and third one it's 1. So C and D do not appear in the name, but A and B do, as in fact A and B. And so we have AB for that prime implicant. Now, do we have any other groupings of size 4 that are not completely contained within the grouping that we already have? And this is a very tricky one to see, but the answer is yes, we do. And it is right here. It's these 2 cells up here with these 2 cells on the bottom. We have to remember that the top edge and the bottom edge of the Karnaugh map are connected to each other, and therefore these 4 1s do form a rectangular grouping of 4 1 cells. So we have that and this. And now try yourselves to figure out the name of that prime implicant. Will A appear in the name? No, because A is equal to 0 on the top row and 1 on the bottom row. What about B? B is equal to 0 on both of these rows, and so B prime will be part of the name. What about C? Well, C is equal to 1 in the next to last column and in the last column, so we have C. But D is changing in those 2 columns, therefore D does not appear in the name. So the name of the prime implicant consisting of these 2 cells and these 2 cells is B prime C. And now we ask ourselves, are there any more rectangular groupings of 4 1 cells that are not already completely contained within a single one of the prime implicants that we have already identified? And the answer is no. So now we go, since there are no groupings of 4, we now go to groupings of 2. Are there any groupings, rectangular groupings, of 2 1 cells that are not already completely contained within a single prime implicant that we've already identified? And the answer in this case is no. And therefore, we're done. These prime implicants, these 4 prime implicants that we have identified, are all of the prime implicants for this function. And now, as usual, once we have identified the prime implicants, then we want to find out the essential prime implicants. And remember that for essential prime implicants, we begin by identifying essential 1 cells. So this 1 cell is essential. This 1 cell is essential. This one is not. This one is. This one is. This one is not. This one is. This one is. This one is not essential. This one is not essential. This one is not essential. And this one is not essential. So, now that we've identified our essential 1 cells, let's identify the essential prime implicants. What about D prime? Well, you can see that D prime has several essential 1 cells, so indeed it is an essential prime implicant. What about AC? That's these 4 cells down here in the bottom. And we did not, notice that we did not identify a single essential 1 cell there. So AC, this is the first time now we've had a situation like this, so pay careful attention. This prime implicant AC does not have a single essential 1 cell, so although it's a prime implicant, it's not an essential prime implicant. Now let's go to AB. AB are these 4 cells, and there is an essential 1 cell there, so AB is essential. And finally, B prime C is the these 2 cells along with these 2 cells, and there is 1 essential 1 cell there, so this is indeed essential as well. So we have B prime C. Now, minimal sums. Okay, again, this function is capital F of A, B, C, D. And remember, now we don't know how many minimal sums we're going to have. I'll just start with just 1 here. And remember, we always start with what's essential. So we have D prime or AB or B prime C. And now we're going to go up and we're going to shade in those 3 terms. So by including D prime in our sum, we have accounted for all 4 of these cells and all 4 of these cells. By including AB, we have included, now you see the advantage of drawing these little sketches over here for AB, just to make sure you see it. You see it's that 3rd row, the Karnaugh map. So by including AB down here in our expression, we have accounted for all of these ones. So let's go ahead and shade them in. And now finally, B prime C. We look at our sketch over here, and it's these 2 cells on the bottom along with the 2 cells on the top. And so if we shade all those in, we have this. And now we ask ourselves, is there anything left, any 1 cells left that have not been accounted for? And as you can see, looking at our Karnaugh map, the answer is no. And therefore, we are done. There's only one minimal sum in this case. And it is that expression right there, f of a, b, c, d is equal to d prime or a, b, or b prime c. That is the one minimal sum for this function. And this problem is important for several reasons. Two of the main ones are that this is our first case with a function of 4 variables. So in other words, it's our first 4x4 Karnaugh map. And this is also our first example where we see that one of our prime implicants is not essential, and therefore it does not appear, or I shouldn't say therefore, because sometimes even things that are not essential will appear in the final minimal sum. But in this case, it does not. But remember, what has to be in the final expression, everything that is essential must be in the final expression. Other terms will be, you'll just have to wait and see. And in this case, that prime implicant AC did not appear in our final expression. So here is the final answer for this problem. And if there was anything about it that seems strange to you, go over this example because it is definitely important.